Hi everybody, Dr. Burns here. We're going to go ahead and start Unit 2, and the first section we're just going to do a little bit of practice with some modeling problems. And we're going to start with just looking at first order differential equations. Later in the unit we'll get into second order differential equations and new techniques for solving those. But I just want to do a few of these. We're not going to get super complicated and crazy with these, but I want to go over a couple of examples with you, and then we'll do a few in class just to practice. So the first one says, consider a large tank holding 1,000 liters of pure water. So the water starts off pure and it holds 1,000 liters to begin with. So there's no salt or anything in the water to start with. A solution of salt begins to flow at a constant rate of 6 liters per minute. As we go through this, pay attention to units because the units are really important on a question like this. The solution inside the tank is kept well stirred and is flowing out of the tank at a rate of 6 liters per minute. If the concentration of the salt, so the concentration of the salt with the water coming in, entering the tank is 0.1 kilograms per liter. So you've got concentration and you've got rate of flow. Those are two different rates there. Determine the amount of salt in the tank, determine when the amount of salt will reach 50 kilograms. So let's write down a few things here to kind of help us keep everything straight. I'm going to start with the amount of salt in the tank at any given time. So I'm going to let x of t be the amount of salt in the tank at time t, whatever that is. Okay? So we need a differential equation that represents this. And I think a simple way to think about this is to just think about it as the rate of change of the amount of salt, so dx dt, is going to be equal to the rate that the salt is coming in minus the rate that the salt is going out. Okay, so the rate of change of the salt is equal to the rate in minus the rate out. And what I want you to think about is how we can get expressions for both of these rates. And this is where it gets a little bit complicated. So that's why I said pay attention to units as we go through these. The rate of the salt flowing into the tank would be, it's not just 6, it's a little bit more than that because that's just the rate of the water flow, not necessarily the salt itself. So the rate of the water is 6 liters per minute, but the concentration for that salt is 0.1 kilograms per liter. So what I'm going to do here is I'm going to multiply this quantity by the kilograms per liter, the concentration of the salt. And notice with those units, you can think about it in terms of what's happening with these quantities. Notice that the liters you can kind of think of as like canceling out, and that would leave you with kilograms per minute. And that would be the rate that the salt itself is entering the tank, not just the water. So my rate in is going to be 0.6 kilograms per minute. That's the rate that the salt, not just the water, is entering the tank. Now, the rate out, let's do the same thing. So the rate out would be the amount of salt in the tank at any given time times the rate that the water is leaving the tank. So the amount of salt in the tank at any given times, do you agree, would be x over 1,000. This is the amount in the tank at any given time. Because remember, x was the amount of salt in the tank, and we started with 1,000 liters of water. And that would be kilograms per liter. And if we again multiply that by the rate that the water's leaving the tank, that would be 6 liters per minute again. And same thing with the units. Notice the liters go away, and I'm left with 6x over 1,000 kilograms per minute. Or if you want to clean that up, we can make it 3x over 500. So notice that the units are kilograms per minute. And that's what we're going to use for this rate in and this rate out. And then we'll have a differential equation that we can solve using techniques we learned in the last chapter. So we have dx dt is going to be equal to 0.6 minus 3x over 500, and my initial condition at time 0, remember that it was fresh water, so there was no salt in the tank to begin with. Now there's other ways perhaps we could solve this. This would be a linear first order differential equation, But I think if we get a common denominator, this will actually be separable. Why don't you pause the video and try it, and then make sure you get the same thing I do. This will be, let me look at my notes here, this will end up being 0.6 is 300 over 500. So this will actually end up being 300 over 500 minus 3x over 500, or just 300 minus 3x over 500. And then if we think about cross multiplication, we get 500 dx equals 300 minus 3x dt. And we'll remember, when you separate the variables, you want to get the similar variables on the same side. So I'm going to divide by this 300 minus 3x term, as well as the 500. So we're going to have dx over 300 minus 3x equals dt over 500. And then, of course, those can easily be integrated. I'm going to skip the details. This would obviously be a u substitution. Let u equal the denominator, and we wind up with negative 1/3 times the natural log of 300 minus 3x equals 1 over 500t plus c, our initial condition. And then I'm going to go ahead and solve for x, because remember, x was the amount of salt at any given time. So I'm going to multiply everything through by -3. So that gives me natural log of 300 minus 3x equals -3 over 500t plus c. I don't need to worry about that because it's a generic constant at this point. Exponentiate everything, and I wind up with 300 minus 3x equals ce to the -3 over 500t. And then if we put in our initial condition of 0, 0, 300 minus 0 equals ce to the 0 power. E to the 0 is 1, of course, so c equals 300. So my differential equation becomes, let's write 300 e to the -3 over 500 t, and then remember I'm trying to get x by itself, so I'm going to subtract 300 equals -3x, divide everything by -3, and we wind up with, let me write this a little bit nicer, x of t is equal to 100 minus 100 e to the -3 over 500t. So this is our model for the amount of salt in the tank at any time t. Now they did ask us, they said, at what time, determine when, so the time when the salt will reach 50 kilograms. So what we're going to do is just set this equal to 50, and I'm going to leave it to you to solve this equation. You don't need to watch me do the algebra here, but I will say that if you do solve this, you should pause the video and practice it. Make sure you understand it. You should get 115.5 minutes. So after about 115 minutes, we're going to be at 50 kilograms of salt in the tank. One more example, and this one's a fairly short example. It's a population model, and it says in 1790, the population of the U.S. was 3.93 million, and in 1890, it was 62.95 million. Using this model, it's the population model, where P of t is the population, t is any given time, and P naught is the initial population when we start measuring it. They want us to come up with a model for this population as a function of time. So if the initial population, you kind of think of it as 0, 3.93 in 1790 when we started measuring, that means P of t would be equal to 3.93, I'm just going to assume everything's in millions, e to the kt. Now on these kind of questions, k is the rate of growth per year. You could be talking about population, you could be talking about bacteria, and in that case it might be per hour or per week or whatever the unit of time is. This is in years. So per year, how much was the population increasing? Well, that's where this other piece of information comes in. We know that 100 years later, the population was at 62.95. So I'm going to put in 62.95 for the population, and I'm going to put in 100 for the time, and that gives me an equation I can use to solve for k rather. If you divide by 3.93 on both sides, I'm getting this. And then we're going to take the natural log, and that gives me 100K over here, and divide by 100, I get a growth rate of 0.0277. And that should make sense for a couple reasons. Number one, it's positive, so that means the population was increasing. And number two, this is about 2.77%, which seems reasonable that the population would be increasing by about almost 3%, I guess, per year over that time period. If I'd gotten 50% or something crazy, that might have been something to pause and look at. But 2% seems about right. All right, I think this is it. We'll do a little practice in class, so bring your notes with you, and I'll see you tomorrow.